Hello, ladies and gentlemen. This is Ms. Fashauer. We are going to continue on in our unit about exponents, but I want to be very, careful as you label your notes because we are jumping into some information from chapter 11. Okay, so in our unit 7, which is all about exponents, we've done 3 lessons about just kind of the basics of how exponents work, and now we're going to start doing some graphing and talking about exponential functions. What would an equation look like with some exponents for 2 variables, an x and a y, that we can start graphing and looking at the patterns there. So our next lesson is called Geometric Sequences, and it comes from chapter 11, but for us it's unit 7, lesson 4. Okay, we have 3 objectives for today. We're going to look at the difference between an arithmetic sequence, which is basically linear, something that might look like y equals 3x plus 5. You graph it. It has a y-intercept of 5. It increases with a slope of 3. It makes a straight line. We did all of that kind of linear business back in chapter 5. But now we're going to start talking about geometric sequences, okay, and how those are different. They are basically exponential functions, and when we graph things, things like y equals 2x, you're not going to get a straight line. Okay, so today we're just going to start scratching the surface of what does this look like as a graph, what does it look like as ordered pairs, and how does the pattern work there. Okay, we're going to try and extend a geometric sequence. Sometimes it's very easy to see the pattern. For example, in this case, we're going to get into it in more depth in the notes, but this would be something that looks like 1, 2, 4, 8, 16. As you can see, things are doubling, so it's not hard to say, oh, it's 32, 64, and so on to extend the pattern. Sometimes you're going to look at it and you're not going to be able to just immediately see what the pattern is, and so we're going to be exploring something called we'll get into the specifics later, but it's basically looking for R. Okay? And then I'm going to give you a formula for a geometric sequence that we can use if it says, here's a sequence, let's find the 100th term. Doing something like this until you have 100 numbers is way too time consuming and not a good use of our time. So we're going to use a formula to get us there. So let's get started. This is a visual of the difference between arithmetic and geometric sequences. Okay, so this first column here on the left side was arithmetic. This should look very familiar. Back when we did linear type graphing, if I have a pattern that goes 2, 5, 8, 11, 14, how is this change happening? Okay, as x goes up here by 1, what's happening to the y? Well, we can clearly see it's just adding 3. Okay, adding 3, adding 3, adding 3. The equation for this type of situation would be y equals 3x plus 1, and the change is very predictable. Each time it goes up by 3, up by 3, up by 3. We could, kind of visualize a line here that's going to increase at the same steady amount, and that change, basically looks like a nice straight line going up. Each time you move over one term here, you add 3. Okay, so in general, in an arithmetic sequence, each term comes from an addition to the previous term. If the sequence happens to go down, maybe we have something, maybe I'll change my table a little bit. Maybe it goes from 10 to 7 to 4 to 1. We talk about that change as a negative 3. Okay, we don't really talk about subtraction too much. You would say the slope here is negative 3. Okay? So if it goes down, we talk about adding a negative, or our change is a negative. Okay? So what is the difference here in a geometric term, or geometric sequence? Here we have 2, 4, 8, 16. You might notice that instead of just a constant addition, we're looking at multiplying each term by some constant to get to the next one. In this case, it's times 2. Okay, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. The general idea here is that each term comes from a multiplication to the previous term. Okay, we're multiplying here. It goes up by a factor, we're timesing by 2. If for some reason we have a situation, and we will actually have plenty of them, where our numbers happen to go down, we go 16, 8, 4, 2, 1, 1/2, and we're looking at how is this changing. We're not really talking about dividing in the same sense that we don't really talk about subtraction here. We talk about this change is being multiplied by a half. Okay, what are you multiplying by? You're multiplying by a half. Okay, to divide by 2 is the same as to multiply by a half. So just to keep it consistent, we say each term comes from a multiplication, and if they happen to go down, we say, well, we're multiplying by something less than 1. We're multiplying by a fraction. What happens when you multiply by a fraction is your numbers get smaller. Okay? The equation, we'll get into the equation stuff many lessons from now, but the equation here is y equals 2 to the x power. Okay, we have a variable here as an exponent. Maybe, if I explain this really well, you might be able to see where that equation comes from. Okay, this isn't really going to be part of something you're going to do on your homework, but I want you to have a general idea of these geometric sequences and how this goes to this for future. So 2, if I look at my output value, all of my y values I'm going to talk about here. If I look at my output value of 2, that's the same as 2 to the first power. 4 is the same as 2 to the second power. 8 is the same as 2 to the third power. 16 is the same as 2 to the fourth power. And you should see a very, very, very obvious correlation between this and this, and this and this. Okay, our term, are we in the first term? Are we in the second term? Are we in the third term? Are we in the fourth term? Okay, our input value here is the same as the exponent on 2. The reason we have that 2 there is because we're doubling. We're multiplying by 2. If we were multiplying by 3 each time, this 2 would turn into a 3. But because we're doubling, we're multiplying by 2. That's that base piece of our equation here. And then the x value here is the same as what is on top of the exponent of 2 each time. Okay? Again, not for this lesson, but important to know where it comes from. Let me summarize. An arithmetic sequence, each term comes from an addition. You're just adding a constant amount. With a geometric sequence, now you're multiplying. Okay, now you're multiplying. You can imagine that with adding, your numbers are going to get bigger each time, 17, 20, but they're not going to get bigger in the same way as when you're multiplying. Okay, 2, 4, 8, 16, 32, 64, 124, 28. You can see how these numbers here get very big very quickly. Okay, and that's a very important characteristic of something that is geometric sequence. Your numbers, as you move on, are going to get very, very big very, very fast. Or if they're getting smaller, they're going to get very small very fast. Okay? So that's the basic difference between arithmetic and geometric sequences. If you're still a little confused, feel free to pause, go back, rewind, listen to something again, and just kind of have in your mind the basic idea that 1 is an addition, whereas 1 is a multiplication. If you understand just that from this slide, you'll be good to go. Let's keep moving. Our next slide here is how can we extend a geometric sequence. For example, find the next 3 terms in each of the following. Sometimes you're going to look at a list of numbers and it's obvious. Okay, this one goes 1, 3, 9, 27. Clearly my pattern is times 3. Okay, you may want to have your calculator out as you do your notes today because these numbers get real big real fast. Find the next 3 terms. All you got to do, 27 times 3, clearly 81, and then multiply by 3, 243, and then multiply by 3, and you're going to get 729. Those are the next 3 terms. Done. Good to go. Number 2. Let's go to number 2. Number 2, you're going to see fairly quickly that the numbers are getting smaller. You might say, first of all, that the first thing that might come to your mind might be, oh, it's dividing by negative 4. Okay, this is the first one's negative, the second one's positive, then negative, then positive. So clearly I must be multiplying by a negative number, or dividing. Okay, so you're dividing by 4. If you said you're dividing by 4, that's totally fine. If we want to think about geometric sequences as always a multiplication, you would say you're multiplying by negative 1/4. which is the same as to divide by -4. Those are the same. Okay, so each time you're going to divide by -4, if that's what you want to punch in your calculator, that's probably much quicker than timesing by -1/4 as a fraction in your calculator. So here, you would say divide by -4, divide by -4, and divide by -4. I don't think we need to take time now to go through and do all of that. I think you would know how to punch in your calculator and go from there. Okay, I'm going to have you guys do number 3. Okay, so pause, do number 3, just find the next 3 terms. It's going to keep going, but I'm going to ask you guys to just do 3. Okay, look for what the pattern is and see if you can extend it. Go ahead and hit pause. All right, if you're coming back to me because you're done, you should be getting the same thing I'm getting here. I'm multiplying by -2 each time. That is our pattern of how things are changing. And hopefully you got those 3 numbers there. Okay, so this is times -2, times -2. Okay, now sometimes you're going to see a sequence where you're not really sure what's going on. Okay, these numbers, not so obvious what's happening. Okay, sometimes it's not so obvious to extend a geometric sequence. What you're going to do in this case, okay, refer to this big red box. And this is an important piece of your notes, so you might want to write down some of these things here. In this case, what you're going to do, you're going to try and find this number here. You're going to find what it is that is the pattern that's happening in each sequence. In our first example, it was times 3, and the second one, it was times, I guess I should circle here, times -1/4, and in our third example, it was times -2. So that's what you're going to try and find. And if you're doing, find the missing number that I multiply by 5 and I get -10, well, then all you have to do is just take 10 and divide by 5 to figure out what that missing multiplication is. Okay, so you could do -10 divide by 5 and get -2. Oh, that must be what I was multiplying by. Okay, if you're trying to figure out to go from here to here, oh, I'm timesing by something. I'm timesing by something. I don't know what that is. Well, division is the opposite of multiplication, so I can divide one term by the one previous to figure out what I must have multiplied by to get that second term. So let's do an example here. Let's do, I'm on that step there, 384 divided by 512. Okay, if I multiply, or if I divide those two, 384 divided by 512. Yes, I'm going to get a decimal or fraction. Basically, this is what I'm multiplying by each time. I'm multiplying by 0.75. This should make sense because the numbers are getting smaller. Okay, the numbers are getting smaller, so the thing that I'm multiplying by has got to be less than 1. Okay, now what is this called? We give this number, this 0.75, or this -2, or this -1/4, or this +3, we give it a name. Okay, this is called the common ratio. Okay, the common ratio. And what does it come from? Actually, I don't need to put the arrow. I have it in the previous step. What does it come from? It comes from dividing one term by the one that comes before it. Any term you want. Okay, I picked 384. I divided it by 512, the one that came before, and I found R. Okay, this is R. So now you know that all you have to do is do 121.5 times 0.75, and you'll get your next term, 91.125. And keep going, times 0.75. And yes, we're getting some crazy decimals in here. That's okay. Just go with it. At some point, we'll probably figure out what we should round to. And then the same thing, we're going to times that by 0.75. Just continue your pattern. And now I'm going to start rounding. 51.23. Okay, hopefully you have that. All right. So just to kind of drive home this point of what is R, what is the common ratio, can you go back and list R next to all of these 3 problems up here? I've kind of already done it for you, but maybe we'll erase this. Okay. Can you go back and figure out what is R? Pause me now. Write down the 3 R equals. For each one of these next to the problem, I'd like you to write R equals, and R equals. pause, do that now, so that you can really check to make sure you understand this idea of common ratio. Your hint is it's not super complicated. We already did this. Just write it down nice and clearly. Okay, I assume you're back. In number 1, r is 3. We already talked about that. R is negative 1/4, and R is negative 2. Okay, yes, I already had them written on there, but I wanted you to write them down nice and clear so that later on, if you want to come back to your notes and say, oh, Ms. Fasher was asking me about common ratio. What is that? At least you have it clearly written down. Okay, if you haven't written down what's in this box, do that now as well. Okay. All right, I assume you're back. We're going to go to our last and final slide. Yes, last and final slide. You're going to see problems in your homework today that say, hey, I'm giving you a sequence, 2, 4, 8, 16. That was kind of the common one we started out with. And I want you to find the 25th term. Yes, in theory, you could continue going on, 32, 64, 100. You could keep going on, and you could list them. But that is not a valuable use of your time. We are smarter than that. We can be more efficient. Okay, so we have a formula to help. I'd like you to take a second, pause me, and write down this formula here, along with the little arrows and colors that say what each item is. Okay, A sub n, that n is, a little bit lower there. A sub n is your nth term. Here. Your first term, we say A sub 1. That's not 2 variables, it's just 1 variable. R is your common ratio. We just talked about that in the previous slide. And then N is, again, the term you're looking for. Example would be 25 if I was doing that first example there. Okay, I'll erase this so it's nice and clean. But go ahead and write down your formula. All right, now that you have your formula written down, let's do some problems. And let's go back to that example there. 2, 4, 6, 8, 16. Now remember, this is my first term because it's written first. This is my second, this is my third, and this is the fourth. Okay, I'm going to start by writing down the formula. A sub n equals a to the first multiplied by r to the n minus 1. Okay, that's an exponent. I want to find the 25th term. So I'm going to put 25 here. I want to, I'm sorry. I don't think that's right. I want to put, let's start with what I know. A to the first term, a sub 1 means the first term, so that's a 2. R, what's happening here? What is my pattern? Here, clearly in this pattern, I'm multiplying by 2 each time to go from here to here. Oh, goodness gracious. To go from here to here to here. I'm timesing by 2, so that's R. All right, we'll put an R here. And then we're going to do 25 minus 1. So I'm sorry, this is not 25. Not 25. That is the number that we're trying to find. A sub n means the nth term. I want to find the 20th term. So that's what I'm still looking for. Like I said to you earlier, grab your calculators. You should have your calculators out. And what we have here is I'll move horizontally 2 times 2 to the 24th. That's really the same. If this is a 1 here, is 2 to the 25th. And we have a calculator to help us out. Yes, it's going to be a big number. Very, very big. 3, 3, 5, 5, 4, 4, 3, 2. Okay, you can see how geometric sequences, things that have an exponent, get very big very, very fast. Did you expect it to be about 33 million when we talked about the 25th term? It doesn't seem to be so big. It doesn't seem to be so many terms. 25 isn't so bad. But yeah, 33 million would be your 25th term. Okay, let's do one more together, and then I'm going to have you do 3 and 4 in your notes on your own to see if you can apply this information. So let's do number 2. Number 2. The first term of a geometric sequence is 128, and the common ratio is 0.5. Basically, it's being cut in half. Each term of your sequence. It's going down by a division of 2 or a multiplication of a half. Okay, so it's getting half as big each time. What is the 10th term of the sequence? Let's just go back to our formula. Okay, if I'm looking for the 10th term, this here is my variable. Okay, the book likes to write a sub 10, so I know that I'm looking for the 10th term. The first term is 128. They tell me that right here in the problem. They tell me that r is 0.5. They tell me that right here. And since I'm looking for the 10th term, I'm going to substitute the number 10 for n. Okay? And from there, it's just really a PEMDAS problem. Just continue to, first you're going to do 10 minus 1, and then you're going to punch that in a calculator, and you're going to get 1/4. Okay, 0.25. Okay? So hit pause right now, please. Hit pause. I would like you guys to try 3 and 4. Wake up. If you're feeling a little bit like you lost your attention, now you got some time to do some problems that'll bring you back with me and see if you can figure out the answers to these 2 problems. Okay, hit pause. When you come back, I will reveal the answers. And first of all, I'm going to fix a little typo. This is number 3 answer. Okay? So, good luck. Hit pause. Try 2 problems. All right, I assume that you're back from trying your problems. Hopefully, you have 648 for problem number 3. If you're not sure where that came from, just follow these steps here. I have everything illustrated for you. Here in blue, they're telling you what they're doing. And then for the last one, hopefully you got, again, these numbers get real big real fast, 32,768. Okay, this problem did not exactly tell you what r was. It made you figure it out. Clearly, if we are multiplying by -2, each time r is -2. Okay, so in this case, r is -2. If you needed that to do the problem, hit pause and take that information and finish. Again, if you're not sure where that came from, simply follow the steps here. Okay? Those are all of our objectives for today. If you're feeling like you want a refresher on any of these things, go back and listen to that section of the video. Remember, our first thing was to understand the difference between arithmetic and geometric. Okay, remember, arithmetic is always an addition as you move along in the sequence, and geometric is always a multiplication. If it looks like it's division, forget it, I don't know how to spell that right now. If it looks like it's division, you're simply multiplying by a fraction. Can you extend a geometric sequence? Can you find the pattern and extend it? And if you don't see it obviously, just by looking at the sequence, can you use r? Okay, even if you can do it, even if it's to see, even if it's easy to see each time, even if it's obvious, I still want you to understand this idea of common ratio. Okay, that's base knowledge we should have. And last but not least, can you use this formula that we just talked about in the previous slide to find a specific term in the sequence where writing it all out, find the 100th term, way too time consuming, much quicker and easier to put it into a formula. Okay? So go back and review anything you need to review, and I will see you in class tomorrow to practice.